Hello, everyone, and welcome back. Today, we're going to be taking a look at an update to one of my most popular tutorials of the last couple of years, which is relative position LiDAR in TouchDesigner. There's a lot to cover on this topic, and I've refined my workflow quite a bit, so I'm going to take you through my latest and greatest, as well as just some understanding of what's going on with LiDAR. Um, But first, let's just take a look at what we're actually going to be working on. So this image here in the background, you can see that's actually a photo of me at Art Basel last year interacting with my own work, where I use all of these techniques to create a very large scale, stunning interactive wall. But for the tutorial, I have a smaller demo set up. I have this real physical screen set up to the left of me. And so as you can see, when I hover over this screen, I'm not only displacing, but I'm also actually turning into monochrome some of the image pixels that I'm hovering over. So this is a very simple effect, but one that I wanted to use to illustrate what we were doing. So if we reset this, and just to show you again, this is the dynamic and interaction that we're after. So with that said, I'm going to turn off our other screen for a second and just go through some of these slides before we jump into the TouchDesigner side of things. So first things first, my name is Lake Heckerman. I'm a new media artist based in Brooklyn, New York, and I explore how technology changes human perception and how we interact with each other. I do this primarily through interactive installations, which I build with TouchDesigner, and I'm fortunate enough to be able to exhibit all around the world. Some of those exhibitions are shown here, including many that I'm using a very similar LiDAR-based interaction for, including this one, Maelstrom, Synapse, and Still Life, all of which I was fortunate enough to exhibit at Art Basel last year. So this is just a sample of how you can use some of these techniques in very large-scale situations. And with that, it's enough about me, and we can actually get into things. So first, just a word, because there are a lot of different types of sensors on the market, and this tutorial is going to focus on receiving the data from SlamtecCHOP sensors only, but then the processing of the data is pretty transferable, and you should be able to use that kind of same process for any type of sensors you have, whether they're SlamtecCHOP or not. So with that said, you should definitely grab a SlamtecCHOP model if you're interested in following along exactly. And I have tested the models that I've listed here with the pipeline, so I'm confident that it works. But there are some other models, and so I just wanted to mention that. I do recommend, if you're just learning, grabbing the A1 as a great budget prototyping model. That's certainly what I would recommend and how I started myself. All right, so what is LiDAR? LiDAR means light detection and ranging, and that's a fancy way of saying basically our sensor is going to be in the middle here. It's going to spin around many, 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 many times every second and shoot out a little laser beam. That laser beam will bounce off of whatever it hits and return to the sensor. The sensor can then use the angle of the beam and the time it takes to return to calculate the distance and location of that object relative to the LiDAR. And that is how relative position LiDAR gets its name. Now, there are other types of LiDAR also that work in similar ways, but maybe are a little bit more complicated. We're going to stick with just this kind of simple functionality because this is the type of LiDAR that we are going to be using. However, I will talk about briefly the other types of LiDAR. So again, the one we're going to be using is a 2D LiDAR called RPLIDAR, relative position LiDAR, that can scan 360 on a plane. So if it's sitting on a floor, it can scan that entire floor, but it'll only catch what is kind of on the plane, not something, let's say, floating in the air above it. Really common for interactive installations. I use it all the time. Low cost, high quality, and we'll get into some of the other benefits later. Some other types are full dome or half dome sensors, which are things like the Ouster that you might have heard of. These are generally 360 or, well, 360 for a full dome and, 180 hemisphere for a half dome. that return a 3D point cloud of a space. There's also photogrammetry LiDAR, which is kind of similar, but generally use drone-mounted and aerial shots for doing things like scanning uh, mountain ranges, topography, forests, kind of like large-scale stuff like that. So it's not always real-time necessarily. Some is. And then, yeah, telemetry or topographic mapping. These are more like a special case of the photogrammetry LiDAR. The photogrammetry LiDAR can be handheld sometimes too. And so yeah, this is just kind of like a drone mounted version of that that's used for mapping big areas. We're not really going to use any of that. We're going to focus on the RPLIDAR because that is great for interactive installations. Why? Well, the primary reason is that it works on any flat surface and you can take as many interactions as your surface can really support pretty easily. That's great because it means that I can have a large LED wall with 100 people touching it, and by setting up my LiDAR appropriately, I should have no problem handling all of those interactions. Generally, these sensors work in a lot of lighting conditions. You can also use Ethernet or just USB connection, which makes it easy. And finally, they're pretty cheap and pretty compact. All of these make them strong choices for me and for commercial installations that I spec out for clients. Very big fan. Now, with that said, there are some disadvantages. This should say disadvantages. Sorry about that. And the disadvantages are mirrors and shiny objects are probably the biggest disadvantage because if you have mirrors, they can disrupt the laser beam and add a lot of noise to the sensor data. One of the other issues is that you can have an object that's occluded by another object. If I have, let's say, my sensor here, right? And there's a person here, that sensor is picking up the person, right? But if there's another person who stands right in between, the beam will bounce off of that first person and will never reach a second person. So a single sensor can often have objects that are occluded from it. You can mitigate this with multiple sensors, but it's something good to know about. And then lastly, or another point, is that again, because the laser beams are going through the air, things like humidity changes and temperature changes in the air are also something to be aware of and can cause some noise. And finally, maybe the RP relative position and planar case of the LiDAR is not necessarily what you need. If you're trying to track someone's hand moving through 3D space, it's not going to work. So those are some limitations or disadvantages of LiDAR. All right, so back to using this in TouchDesigner. A lot of LiDAR, or not a lot, but a few LiDARs have native support in TouchDesigner with operators. These tend to be pretty expensive, and so I think it's great to be able to use some non-native supported sensors like the SlamtecCHOP edition or the SlamtecCHOP models. With these, there's just a little bit of additional work. So one of them is installing a driver, which we'll go over. There's also a C++ wrapper or like a plugin that's required to actually interface with the LiDAR data. Thankfully, some lovely developers on GitHub have created these already, and we can actually just grab fully built plugins, which we'll also go over in a second. And, well, that's really it. And then finally, we'll have a chop that we're going to have to then process and actually kind of convert into a usable texture for our installation. Final piece will then be mapping, and this is the part that's somewhat transferable across all different types of LiDAR. And so generally what we're going to do is take our LiDAR as chops and instance and render that data, and then actually crop this render down to the relevant real-world space based on our screen so that we have a nice mapped interactive LiDAR display. A couple things I wanted to note in case you have problems. One, make sure you have that driver installed. I'm going to get to it in this next slide and show you how to download it. Definitely make sure, check that several times. You can also check that you have your driver installed by going into your device manager here and checking on the ports, COM and LPT, and making sure you see one of these Silicon Labs CP210X, etc. COM ports. You'll also need this port to configure the TouchDesigner operator. So that's a good way to verify that the driver is working. And the other thing is make sure that you have a USB cable that supports data and power. And finally, make sure that you fully unwrap the LiDAR, cleaned it off if it's dusty, and that there's no issues there. Okay, so we need then to figure out what driver we need. I'll put these in the description and make sure that there's links, but give me 1 second and I will pull up the descriptions here anyway. Okay. So this is the direct download link for this driver. If I just go back to, okay, USB UART bridge driver. There we go. This is the one that you need. And you go to downloads, and then you download the driver from here. And I'll put a direct link for the download in there. And then the other thing that we need is the C++ plugin. And so that will be here at this GitHub repository. We just need this download this DLL file. So those are the two things you'll need to make sure that we can follow along with the rest of this tutorial. And so now we can jump into things. So what will I do? I will bring the display back up. I will also just move it over here so that we can see the parameter window. And all right, now this LiDAR, this is the component that we're going to be working with. So I'm going to get rid of, well, let's get rid of all of it. And we'll just restart this from the beginning. So the first thing you need to do is grab a C++ chop. Well, the first thing you need to do is download and install that driver. And then plug in your device, make sure that it's working, make sure that you can see the COM port here. And then we'll use a C++ chop. We will find the plugin path, which will also be available in the project files for my Patreon to download, so you can just get all of this in one foul swoop. But we want to associate this SlamtecCHOP v3.dll with our C++. This is the plugin that will let us load the data. Then LiDAR settings. Don't touch this at the moment. We want to go to our connection settings and make sure that this COM3 is set to whatever the COM port is in your device manager. So in my case, that's COM5. Now, COM5, then I'll go back to my LiDAR settings. I'll turn it on active. You'll see that some motion or just occurred. It looks like there's some data coming through. There's a couple of things I got to fix. One, I want to go to my output settings and change this to 10. The reason for that is this is minimum distance, maximum distance. So if this is set to 0, we're not really actually getting any points. But set to 10 meters, this will give me any points between 0 and 30 feet from my sensor. And then I'm going to change this to Cartesian. You don't necessarily have to, but I like it. Okay, then we can see that this data live feed is coming through. If I come over here, you can see kind of this data moving as my hand is touching the screen. So that's great. Then what I'm going to do is just select. I'm going to select my X and Y channels. I'm going to use a transform XYZ. We'll get to in a second. And then a null, and this null I'll call P. So this is our LiDAR data. It is really that easy. And before we can really understand what's happening, we're going to need to render. So I'm going to drop down an add. I'm going to add points. I'm going to drop a convert. We'll convert particles per point. Then I'm going to add a geo. Turn instancing on my geo on. I'll use my P for my translate op, translate X and Y points. I'll then use a point sprite material on there, and I'll use a circle top with a little softness as the texture for that. Then I'll drop a render down with a null, and then the last thing we're going to need is a camera and a light. And so there we have our whole render all set up. I'll turn this point scale way up, and now let's see. We don't see anything in our render except for this, but if I really zoom us out, we can start to see some points. And so maybe we need to just adjust a little bit our geometry. So my render, I'm going to turn to 2048 by 2048 square aspect ratio. My point sprite, we'll turn blending on, make our life a little easier. And then this constant point scale can be like a lot bigger. Okay, now, generally, the process that I like to follow here is get this raw data and in some way center it on the renderer. Now, you can do this either by changing the uniform scale on the geometry or maybe the camera itself. You could do like zoom out the camera quite a bit or a combination of these. It's going to depend a little bit on your setup, and that's okay. So here, this is, okay, so now we can see kind of our room, if you will, because my LiDAR is set up on the screen. And so as I'm touching the screen, we can see that dot, that's my hand right there, moving around. Now, as my hand goes up, the dot's moving down, and that is why we added this transform, because sometimes we're going to need to rotate. So I already have some parameters up here on my parent, and so I'm just going to associate these really quick. You can just create them, obviously. And the rotate is what we're going to want on our transform. So I'll go to transform, XYZ, and then we just have to figure out how to rotate. And so if I rotate on my Z-axis, that looks like what we want, and 180. So I'll drag and drop this, and so now I can use this rotate to rotate my render. And the reason this is really helpful is every time you install your LiDAR sensor, the rotation might be a little bit different. And so it's nice to have a slider to be able to just kind of like use that. I also have a constant point scale that I use for the point scale render, and that's also just nice to be able to adjust. And then finally, this resolution, well, I'll get to that in a second. So, okay, the last thing that I wanted to mention is sometimes you'll see the LiDAR data, and it'll just stop. It'll just stop just like this. I just unplugged it to make it stop, but sometimes it might just happen if, let's say, somebody like rolls a scissor lift over your USB, something like that. So anyway, if this does happen, this re-init is generally what we want to hit, and then we kind of see the whole C++ chop reload. So that's what I have this pulse parameter on my parent for, and that will help me just quickly be able to reinitialize this if I need to, if there's problems with my data. So make sure you don't actually reinit it if it's running, because that'll mess things up, but I will just unplug it, plug it back in again, and we'll re-init this. Okay, so now our data is going. We can see it. Okay, so now for some of the mapping, I'm going to just translate my geometry. I'm going to try and center it a little bit. And then we'll use the uniform scale on our geo. And so basically what I'm trying to do here is just, as much as I can, center our world space, real world space, on this square renderer. That's pretty well done. And so at this point, now we start to do kind of like the mapping process. So I'm going to give an out to myself, go up, and I'm going to just bypass actually this whole thing. So now we can see my LiDAR coming out on the screen and my reflection. Hello there. So I'm just going to try and make this a little less reflective. That didn't do a ton, but yeah, whatever. We can see the data. It's all messed up, obviously, because it's my entire room, and so we're seeing a lot of stuff that we don't need, and there's clearly like this area in the center that is our visual reference. So to isolate that, simple, manual, and pretty hard to mess up, literally we're just going to be using a crop. Now, the other thing to check is sometimes the lefts and the rights might be flipped, like in this case. So I'm going to insert a flip. I'll flip my X. So now when I go up, I'm going up. And when I go left, I'm actually going left. That's great. Now we just need to crop it to the actual screen. And so for this, it's pretty easy. I'm going to take my hand, and basically have my hand right here. And then I'm going to crop, what am I on, the left side? So I'm going to crop the left side of my texture, and you can see as I move my hand up and down, I have that dot that's moving, right? And I'm just going to crop right until this guy is right on the edge, right where my hand is, okay? And then I'll do the same. I'll go to the bottom. We'll crop the bottom to right here. Now I can go, it's kind of hard to see it. On the right side. And then finally, pardon my reach, we'll do it on the top. And I'll just move it a little bit, and right there, right on the top, just like that. And so now I can check myself. I can see that as I move around, my hand is really being tracked quite well. And that was really fast, wasn't it? Now, one thing is that this crop is kind of a weird aspect ratio, and not necessarily exactly the one that we want. So I'm going to, right after it, just apply a fit. And I'm going to fit this to the resolution that I have as a parameter. And this will ensure that it is fit to exactly the aspect ratio of the screen. And the reason that that's totally fine is because this screen is the aspect ratio that we're outputting to, right? So like our world space aspect ratio and our screen space aspect ratio are the same. And whatever weird, not perfect aspect ratio in the crop is just because our cropping is a little imprecise. And so we can sort that by having a fit, and then boom, we're really nicely aspect corrected, except right here, you can kind of see that it's cut off a little bit. And that's because our fit should be set to fill. And there we go. Now I have a really nicely mapped screen. So that's great. Now I can connect my image back, and I can connect my SlamtecCHOP LiDAR to my image. And if I have both of these here, okay, yep, just like that. All right, so yes, now I have all of this set up, and so now my simple displacement and look at that. In, I don't know, less than 10 minutes, I was able to take that sensor, map it, and have this fully interactive art piece. Now, obviously, this displace is just a very simple effect that I took from my recent Mastering GLSL and TouchDesigner course. So you can grab that on my Patreon if you're interested in this effect exactly. But this can be anything, right? There's not necessarily any reason that it needs to be this. For example, we could do something really simple and just do like a feedback with an add and output this instead. And now all of a sudden, I'm drawing, right? So this brings up the last thing that I want to talk about, which is moving really fast. You can see this gets a little bit clumpy. And so sometimes if I'm doing something like this, I'll want to have some sort of like a blur in the feedback loop and maybe even as like a post-processing in my render. The other thing is turning up the render size can help. Which just brings things a little bit more smooth, and I tend to like that. But anyway, that is about all I got for this update in LiDAR. There's a lot to learn from this. There's a lot to experiment with, and I'm excited to be able to share some of this with you guys. So some final notes. All of this will be available on my Patreon. The LiDAR LiDAR data processing and mapping talks, as well as this displace effect, and also the DLL file itself. So you can get all that on my Patreon. Thank you for following along. I hope you guys enjoyed and found this helpful. And if you're interested in learning more, subscribe on my YouTube, and check me out on Patreon. I got hundreds of TouchDesigner tutorials covering everything from GLSL to interactions to you name it. So with that said, thank you for watching. Thank you for the support. And until next time, I hope you have fun out there.